What is Kiji? Kiji is an open source modular framework for collecting, analyzing, and serving entity data in real time. So a little bit about the history. It was built on top of HBase Hadoop using Avro as a serialization library of choice. And then recently reintroduced support for Cassandra. It's in beta. So the motivation behind Kiji was, folks from Cloudera, Google, who started Weeby Data, realized that the infrastructure needed to build out systems such as recommendation systems or personalized search required technologies like they had at Google, namely GFS, MapReduce, Bigtable. And hence we have the open source equivalents, Hadoop, HBase, and HDFS. But unfortunately, there wasn't the infrastructure needed to build applications on top of this. The ability to define table layouts, the ability to serialize and deserialize complex records, the ability to process this entity-centric data on top of HBase in a MapReduce fashion, hence the birth of the Kiji project. So the outline of the presentation will be as follows. First, I'm going to give a little bit of motivation behind Kiji, more than what I've just mentioned just now, how it works, just a comprehensive overview of how Kiji works, a bit more about the data model. This is something that I think is very, very important for everyone to understand, is the data model that is Kiji, what it means to evolve data, the data evolution inside of HBase, batch processing using Kiji Express, and then finally real-time scoring. At any given point during this presentation, I don't want to be talking at you. I want to be having an interactive conversation. If you have any questions, please ask, and I'll answer at the time. So who's using Kiji? As you see with our schedule, we have two keynote speakers, or two awesome presentations. Macy's is using Kiji in production for personalized recommendations, and O-Power is using us, amongst other things, for producing energy insights and helping the world save energy through the use of big data. So a little bit about motivation. Say I'm a retailer or a customer wanting to build out personalized recommendations. And I only have an engineering team, a bunch of logs, a Ruby on Rails app, and a MySQL database. And I have a team of data scientists who understand R and Python. So the question is, how do I get to my end goal? So I go to the local Hadoop store, and I pick me up a locally sourced, organically grown, sustainably built Hadoop. I come home, open the box, and I've got this. I've got Avro, HBase, Hive, Solr, Pig, Hadoop, maybe a Cassandra thrown in there depending, which allows me to take logs plus MySQL and ingest it into my big Hadoop data warehouse, which is great. But I still need a mechanism for my engineers on my Ruby on Rails app to request recommendations trained by my data scientists so I can serve them back to my front-facing website for my customers to purchase more stuff. So I go back to the Hadoop store, and my friendly sales rep says, try a Kiji. I'm like, sweet. So I come home, open up this bento box, and I've got Express, MR, Schema, Hive, Scoring, and REST. I'm like, sweet. So I'm like, well, how does this work? So fundamentally, Kiji is a storage system that allows you to store entity-centric data. And it bridges the gap between two organizations in your company, engineering and data science. And your engineers care about writing and reading data from this entity-centric storage in a clean mechanism with clean APIs and setting up data plumbing. On the flip side, your data scientists care about asking questions in a language of their choice and analyzing those answers in a tool of their choice. So let's start with the engineers. So engineers are interested in ingesting data from a variety of sources. You've got web, mobile, wearables. And usually this data is stored in either relational databases or large flat files, access logs, if you will. And so if I want to bulk ingest all of this data into Kiji, I will use something like MapReduce. And using KijiMR, I can batch process all of my logs and my databases and produce maybe H files or another mechanism and just throw them into Kiji and say, here. Alternatively, and this is what we kind of talk about here at Weeby Data, is instead of batch processing on a regular basis, why not stream this data directly via Kiji REST or any other mechanism, but let's say Kiji REST for now, into HBase so that your recommendations can be generated based on the most up-to-date interaction. And likewise, using Kiji REST, simple RESTful APIs, utilizing the HTTP verbs, you can get back information from Kiji in a nice, friendly JSON response that can answer questions as simple as, what were the last 10 interactions for a given user on my website? What were the recommended products for this given user for my website? So now, the storage system, as I mentioned, is called Kiji Schema. And Kiji Schema is what kind of helps you go down this design pattern of what we call entity-centric data. And when we say entity-centric data, it means that if you think about your organization as a giant Excel spreadsheet, where each row is a given user, and all information about that user is in one row. All of your click history, your purchase history, your previously shown recommendations, or if you're a networking company, that might be a router ID, and maybe all the incidents that have happened for that router, or whatever you think of as a single entity in your system, and you basically co-locate all the data associated with that. That's what we consider a single row. So all of the data associated with a given row is stored in this one row, and it's stored in different columns. So I can have interactions column, purchases column, recommendations column. All of that is co-located inside of a single row. So now let's shift over to the data science side. As a data scientist, you want to query this information. So all of the information about a given user for all of your 100 million users is stored inside of this one rich data source. So now the question is, well, how do you get data out of this? Well, one simple answer is, well, I can use SQL. And in Hadoop community, SQL is generally represented through Hive query language. So I can execute SQL-like queries on top of this rich data store and get back my answers. And some examples of this might be, give me the top 10 most frequently clicked products in my catalog. Give me the last top 10 most frequently shown products in my catalog. Or give me the top 10 products that have the least impressions shown on my website, so I can maybe increase the diversity, or I can get a skew of what's the product impression distribution or something along these lines. I can execute those type of simple queries inside of Hive to just get back some basic information, some basic analytics about my data. And whether you choose to use tools like R or SAS or Python, you can still interact with things like Hive to get those answers back and process them how you wish. Now, a more flexible, or maybe on the other side of the spectrum, is KijiMR, which is basically the Java API for MapReduce to be able to ask these arbitrary questions of this data source using Java code. And this is great because in KijiMR you have the benefit of getting out-of-the-box recommenders, item-based collaborative filtering, k-means clustering, and naive-based classification. So KijiMR is great. If you have a Java-based data science team, you can write raw MapReduce. The world is great because I can run MapReduce jobs over my entire data set, as opposed to downsampling this into something like R or Python, and get better insights because I'm running jobs over all of my data instead of just some of my data. So now we've got Kiji Express. So you've got Kiji Hive on one side and Kiji MapReduce on the other side. Well, what Kiji Express allows you to do is express complicated MapReduce flows using a simple Scala DSL built on top of Twitter's scalding. So now, instead of chaining together multiple MapReduce jobs, you can build these expressive flows inside of scalding and let the scalding workflow chain these jobs together to execute a functional unit of what you want to do. So an example of this might be, I want to do item similarity using cosine. Similarity is the metric. And it needs to do a matrix multiplication. So scalding has a matrix API. So in a few lines of code, I can get item similarity matrix using cosine similarity. I don't have to write all of that in raw MapReduce. So now, if you look at the two axes of power and usability, you've got KijiMR on one side and Hive on the other. But regardless of which option you choose, all three of these gives you the full power of in-Hadoop analysis over all of your data. So now, I've ingested my data through MapReduce or REST. I have a data scientist whose team has produced a great model with awesome insights. I now have to take those insights and make them translatable to something that's used in production. In other words, I need to score or produce recommendations of these insights that affect production. So how do I do that? Well, that's what we call a scorer. A scorer is what takes information about a user's current context, maybe their recent click history, recent items that they've added to the cart, combine that with the insights generated by the data scientist, and that produces a score. And a score can be, an example of a score might be the top 3 product recommendations for a given user. Will free shipping increase the likelihood of conversion for a given user? So forth and so on. And the results of these scores are stored inside of HBase as a derived column alongside everything else. So again, this goes in line with the everything about a user is stored in that same row. So you might have a recommendations column that contains all of the recommendations for that given user. And now you can argue that, okay, I can produce all of my recommendations for all of my users, all 100 million users in batch once a day, once a week or whatnot. And that's fine, that works well. But we believe there's a better way, which is you should be able to produce recommendations for users in real time as they request it based on the most recent interactions. So the way we get to do this is a data scientist can deploy their model to what we call the model repository. And then you can attach what we call fresheners to a column in Kiji that says, when you request this column, and if some condition is true, say that condition is a user clicked on a product recently, or the last time I generated recommendations was some time in the past, recompute recommendations, and then return those recommendations back to the user, and store those results into HBase so that you're not you're not always executing these recommendations. Or you can choose to execute recommendations all the time if you want. If you feel like every time you ask for recommendations, always recompute, and that's also fine too. We give you the flexibility to do both. It's basically read-side triggers. So now you have, this completes the whole loop. You have models that you have trained, you've stored in the model repository, you've attached a freshener to it, you have Kiji REST that makes a real-time request, and it flows through an entire Kiji system producing scores for your users. I think I've gone through some. So just in short, for engineers, Kiji allows you to ingest your customer data from any channel, any source. It provides a unified API for reading and writing these customer attributes, events, or insights derived from data science models. And for data scientists, this allows for the integration with existing tools, such as SQL through Hive. It provides in-Hadoop analysis using Kiji MR or Kiji Express. And it allows you to deploy models to production without requiring re-engineering of your models, or in some cases without requiring engineering at all. And for more information about what I just talked about here, please see us during office hours. So now, the next part I mentioned was the data model. So as I mentioned, Kiji table is the kind of the highest level unit of work. And a table is broken up into multiple rows. And each row is uniquely identified by what we call an entity ID. And an entity ID can be componentized with multiple types for their different components. So whereas in maybe just raw HBase, you might have a string primary key, and you have to manage what these components are, break them apart, and typecast them as you need to. We support having multiple types on different components, so you can semantically break up your entity IDs into something that makes sense. And on the data side, the data is broken up into different column families, which is sort of a logical grouping of data. And at the next level, you've got qualified columns, which allows you to identify a piece of data at the lowest level. So I can have an interactions column family, and within those interactions, I've got clicks, I've got impressions, I've got searches, I've got page views. So I can kind of logically group my columns together. And to support this whole notion of all of your users' data historically associated with a single row, we have to have support for, and this is where Kiji has and HBase has support for timestamped versions of cells. So if you want to show the last 10 interactions for a given user, you go to the interactions column and request the last 10 versions. So you can imagine now this multidimensional database. And to add more complexity, but more fun, is the ability for complex data types. So rather than having a column that just allows for ints or strings, we support the concept of Avro objects, so nice, rich, complex objects stored at the cell level, so that my single click record has a product ID, a session ID, and maybe a device, a mobile device or an iOS device that constitutes this click. Are there any questions so far before I continue? Okay. So now the physical organization of data in Kiji is at the locality group level. So the locality group clumps together different column families physically on disk, and you can define properties of these locality groups, such as how many versions to keep around, what's your time to live, whether or not it's compressed, and whether it's not it's even in memory or even on disk. So for an example, if I'm doing lookups on my recommendations column, I want to keep those in memory as much as possible because I'm expecting to make a lot of requests for recommendations. But if I'm making a request for the information metadata field, I might not do that very often. That might be done when I'm computing a score, which might be once every, let's say, half hour. So the frequency of interaction or the frequency of requests impacts how you customize the locality groups properties. So each row represents a single unit of transactional consistency, which means that all writes to a single row are basically in a single transaction, and I'm guaranteed consistency for data written to a single row, which is actually very important because if you want recommendations to be dependent on the most recent interaction, you need this level of consistency. So as I mentioned, a locality group in Kiji correlates or corresponds to an H-base column family. And we store all of the Kiji column families as encoded H-base column families. So you don't have to worry about problems such as, oh, I need to make my column families as short as possible because if you recall in H-base, each cell is a row, is a row key, column family, qualifier, timestamp value. And so typically it's the case that you want to keep your H-base column families as little as possible to reduce disk space. Using Kiji schema, you can make your column families as long as you want. We will translate them to a single byte or a single 2 bytes. So we maintain that mapping for you. An entity ID in Kiji is the same thing as a row key in H-base. Again, you don't have to worry about things like hotspots because you can provide hashing properties. So if you want to have nice uniform distribution of data across your cluster, you can specify how many bytes of entity ID that needs hashing. As I mentioned, you don't need to worry about things like the types of the components within a row key because you can specify some types. So you can say, I want my user ID to be an int, and I want my product ID to be a string, and we will enforce that and ensure that's the case. So you have strongly typed entity IDs. And as I mentioned, column values themselves are bytes. They're bytes, and we use Avro as our serialization library of choice because of evolvability, which I'll talk about later on. So just a summary of the data model is Kiji is an entity-centric data store with componentized entity IDs as the row keys, the primary keys. We encourage wide flat rows, encapsulating all information for a given user. And we allow per row scoring and analysis in real time. And again, for more information, please don't hesitate to ask us during our office hours. So data evolution. This is always a fun topic. Big data applications evolve over time. That's just a fact. I mean, all applications evolve over time, and that's just a fact. You need the ability to evolve your data and your applications without necessarily bringing everything down, running an expensive migration, and bringing everything back up. That's just not feasible always. So for an example, let's say I have a user information record, and it has 3 fields, a name, an address, and an age. But I need to migrate this to a more fine-grained user information record, one that has a first name, last name, and age, an address and age. So how do I do this? Well, in the early dark ages, I'm going to execute some expensive SQL statements. And in most SQL databases, you will have to probably bring it down or lock the table while you execute a few expensive alter tables, write some code to convert the name to first name and last name, and then drop the column, all of which are very expensive operations. If you have 100 million rows, you're doing this execution over all of your 100 million rows. In the latter dark ages, I will have a JSON record or some other SON record that has a name and an age. And I'm just going to write first name, last name, and a new age. It's NoSQL. I just write whatever I want, right? And let the applications deal with the rest, okay? But in the Renaissance, we use Avro, which means that I'm going to declare my Avro record with an optional name. And I'm going to evolve that Avro record to have a first name and a last name. And I'm going to use, because I'm using Kiji and its schema defensiveness, I will make sure that the schema that I'm proposing, the one with the optional first name and last name, is compatible with the schema that I was using previously so that my applications don't break. And what this means is I'm no longer at the application level doing any crazy checks in my JSON or whatnot to say, well, if the name exists, then I know I'm in version 1. Else, if the name doesn't exist, then I might be in version 2 and have these really crazy branching statements. I don't have to do that anymore. I just rely on Avro to take care of that for me. So an example schema DDL statement might look like the following. I have a users table with a row key format where I have a user type, which is a string. So maybe the user type is whether I'm logged in or not, or what device I came from. Maybe my user ID is a long, because I know that's what my user IDs are. I have a single locality group, and I have an information column with my user metadata Avro record that I talked about before. So now in summary for data evolution, Kiji keeps track of your schemas. We keep track of what schemas you use to read with and write, and read from and write with. We ensure that these readers and writers are compatible with each other when you write data to Kiji so that you don't shoot yourself in the foot. And we relieve your applications of the burden of managing these schemas. And again, for more information, you kind of know where to find us. Please talk to us more in depth about this. So now, batch processing via Kiji Express. As I mentioned in the how it works section, Kiji Express is the marriage of Kiji APIs and scalding. Scalding is a Scala-based DSL written on top of cascading. And for those of you that are familiar with cascading, it is a Java-based API that allows you to express complex MapReduce workflows, thinking in terms of pipes and tuples and aggregator operations and mapping operations. And scalding is a Scala-based DSL on top of cascading, making it easier for you to write these applications. And Kiji Express, therefore, allows your analysts and engineers to define these complicated workflows to build and train machine learning models. So an example, and I won't go in detail on this, but you can see in about, I don't know, 10 lines of code, I've been able to ingest a large, let's say, a terabyte worth of song information. Let's say it's a tab-separated song information with a duration and a name. And I can emit an Avro record and dump that into Kiji. And so the equivalent MapReduce code would probably be significantly longer because I have to write multiple MapReduce jobs and chain them together somehow. So the benefits of Kiji Express is that it provides extensions for scientists and engineers to write ML models with pipe extensions such as cosine similarity, TF-IDF, et cetera, using our Kiji modeling package. You can output data directly to H files through Kiji Express, much like you can with Kiji MapReduce, allowing for bulk loading, some of the stuff that you probably heard about yesterday at HBaseCon. We also provide simple APIs for sourcing and syncing data into and out of Kiji, and we have support for packing and unpacking Avro records while processing. So now the last section of this talk is about real-time scoring. And this graph kind of shows you the motivation behind real-time scoring. Why do you want this concept of real-time scoring? Well, if you think about if you run your recommendation algorithm over all of your user set every single day, the chances are that maybe 10% of them will actually benefit from this recomputation. And you're just wasting compute resources on processing 90% of your users. So instead of doing this in batch, why not do this in real time as your users are coming back to your site? So when a user comes back to your site, They may have added something to their cart recently. They may have clicked on something recently. So while I then go back to my product detail page, I make a recommendation request, I can use all that information to produce new recommendations and serve that back to your users. And so therefore, again, as I mentioned, these are read-side triggers that I've attached to my columns so that I'm not wasting valuable compute resources in batch every night. So recommendations should be able to be refreshed based on the most recent user interactions. I should be able, certain data, such as item-item similarities, probably won't change very often, but the user interactions will change often. Therefore, the kind of the intersection or the multiplication of these two resources should be done in real time. Kiji provides facilities for both. So Kiji scoring is a framework that allows for the lazy evaluation of models. It uses HBase as a cache, storing the computed values only recomputing when necessary and storing when done. So some terminology that you'll probably hear throughout is the concept of a freshness policy, which is when do you actually when do you trigger the execution? We have a freshener, which is what actually executes the scoring logic, and the score function is what the freshener uses to execute your actual recommendation code. So in summary, Kiji scoring allows users to bind triggers to columns. You can define different evaluation criteria on when you recompute values for a given user. And you avoid the recomputation of recommendations across all of your users. Only 20 or 30% will actually take advantage of this. So in conclusion, Kiji contains components to allow the engineers and data scientists to store data in an entity-centric model. You can build and train machine learning models and score models on a per-user basis in real time when requesting the row. I think that's all I have. Is there anything I can answer for you?
Is it open source?
Yes. Kiji is fully open source. You can visit our website at kiji.org. You can go to our GitHub page, github.com/kijiproject, and download and explore the source code. The fastest way I suggest to get started with Kiji is to download the bento box. I think, yes. If you go to this table, you can get a sheet on the Kiji project, which has a getting started in 2 easy steps. So I highly suggest everyone go and do that. It's very easy to get started with some of our tutorials, building a recommendation engine yourself, and get understanding more about what I described here. And the question was, where are we focusing Kiji in terms of, are you asking independently between recommendation, classification, and clustering? I don't think we're going to pick one of those and focus on I think we should focus on all three. So right now we have a lot more work in recommenders because that's what we feel a lot of folks need right now. But I think next steps will be clustering and classification. That's a good common question about integration with other open source technologies. The answer is yes. We would plan to explore those integrations where we can. In some cases, it may not make sense, but in a lot of cases, it would make sense. A good one would be Spark, I think, is a great place to integrate. Storm is another great integration point where we can take advantage of some of the real-time streaming systems that those guys provide. We don't preclude integrations with those. We just haven't invested that time yet. Well, enjoy the next half hour. Please eat, drink, chat with us more. I think the next presentation starts at 2:30, and I'll be, along with everyone else and my colleagues, will be here to answer any questions that you have if you want to have a more private discussion. But thank you very much for listening.